Today we'll be talking about time harmonic fields. And how Maxwell equations apply to that. First, it's a good practice to review some complex number or phasor x, which has a x and y, which is the real component and the imaginary component. It can also be written as r for the magnitude and phase phi, or the z phasor can be written as r e to the power j phi, which is also equal to r cos phi plus j sine phi, using Euler's formula. Now we all know j equals square root of minus 1, the imaginary value, and r is the magnitude of z, which is equal x squared plus y squared. Now we should note that x, y, z, r, and phi, that they are not the coordinate variables. However, if you look at it in a graphical way, you have the real and the imaginary. The r is here, and then you get the y and the x values, and you get the phi here, and this rotates at an angular frequency of omega radian per second, and this is your r. You can relate this graphical image here to relate all these variables together. Now, usually z equal x plus jy is referred to rectangular form, whereas z equals r with a phase angle of phi is referred to as polar form, or obviously r e to the power j phi. Now if we introduce time element, so by letting phi equals omega t plus theta, and where theta is, obviously you have the time element here, and then the theta can be maybe a function of time, space coordinates, or even a constant. So z now will be equal to r e to the power j phi, which is r e to the power j omega t plus theta, which is also equal to r e to the power j omega t e to the power j theta. And here you see your time component. Now the real of z will be as follows, which is the cosine of omega t plus theta, and the imaginary of z will be represented as follows, which is equal r sine omega t plus theta. So that's a brief complex variables, complex numbers review. Now we get, for an example, if you have let's say a sinusoidal current with a magnitude of I naught, you'll have e to the power j omega t, e to the power j theta, and let's say we drop the time factor or time component or the time factor e to the power j omega t. We'll end up with I naught e j theta. Usually this is referred to as the phasor current, and some textbooks use IS, others use I tilde. We will use the IS notation for this mini tutorial. And also it's important to note that I of t equals I naught cos omega t plus theta is referred to as the instantaneous form, or you can say I of t taking the real of the phasor current multiplied by the time component. So you can see how the instantaneous form is related to the phasor. Note that a phasor can be a constant or scalar. Can be a scalar or vector. So let's take a vector A. This denotes a vector that has the spatial component and the time component. This makes it a time-harmonic field due to the sinusoidal time-varying nature of that vector or signal, and the phasor form, or the phasor form of A is obviously AS. We can put here to denote the vector that only has the spatial coordinates. Now the instantaneous form of A would be equal to the real of that phasor and e to the power j omega t, which is the time factor. Now let's look at an example. If A equals A naught cos omega t minus beta x going in the y direction, so obviously the instantaneous form will be a real of A naught e to the power minus j beta x multiplied by j omega t. Now compare that to the general form, which is AS, which is the phasor, e j omega t. We can obviously denote AS, which is the phasor component. This phasor component is equal to A naught e minus j beta x going in the y direction. Here I should have added the y direction right after the spatial coordinate. note it's here, not here. Now, it's sometimes very important to get the derivative of like the time derivative of the instantaneous quantity, and it's useful usually in Maxwell. You know, there's a time derivative usually taken for electric fields and magnetic fields. So for now, we say if we take the time derivative of A, what you'll end up with, obviously, the j omega goes down because you're taking derivative, the phasor component and the time factor. So you can say that taking time derivative of the instantaneous quantity is equivalent to multiplying its phasor form by j omega as follows, right? And similarly, for integration, you have division by j omega. We analyze this using the real part of vector A. However, we could have done the same for the imaginary part and solved it from there. But for this example, we use the real part. So the major differences, or the major points we just made about instantaneous and phasor forms are as follows. If you have a vector with x, y, and z and the time, and then the phasor is just the spatial coordinates, the instantaneous form is time dependent, as you can see, and it's real, and it's denoted as follows. Ej omega t. Whereas the phasor A is time invariant, and usually it's complex. It's a complex value. Now let's relate this to time-harmonic Maxwell's equations. So in point form and integral form, I'll just silence my phone. Alright, so you have the Maxwell equations as we know them. Divergence of the electric field component, but now since we work on phasors, note that we will the e to the power j omega t component will cancel out because it's in every it's in every equation on both sides. So the d, that's why we can justify working with phasors. So the electric field phasor form equals to the charge density phasor form, and the integral, of course, will be integrating over that surface for the and then the integrating the total charge density will give you the total charge enclosed in that volume. So that's the first one. The second one, which is divergence of the magnetic field in phasor form equals to 0. And that's like saying that's as if because it's dipole, it's not monopole. That's like saying the charge of the magnetic charge's density is equal to 0. And you integrate that magnetic field, you get a 0. Now the third Maxwell equation, you have the curl of the electric field in phasor form equals minus j omega of the magnetic field phasor form. Obviously this is the phasor form, that's why you have the j omega. We used to know it as minus time derivative of the magnetic field. However, doing phasors, as we have seen earlier, it's like multiplying j omega with the vector. Now the integral form will be as follows: equals obviously minus j omega magnetic field. Part 4, which is the last law of Amperes, which is called Amperes law, Maxwell's equation. You get the conducting value, current density, and now it's in phasor form, plus j omega again, and the phasor form of the electric field component, which is really the electric flux density. However, we used to know this as, again, the time derivative of the magnetic flux density, but now we're working with phasors again. So the integral form will be as follows: we should note that the electric flux density is equal to the permittivity epsilon multiplied by the electric field component, and we're working with phasors. So we can say that the last Ampere's law can be equal to J, which is the current density, plus j omega epsilon and the electric field component. And epsilon here is equal to the relative permittivity multiplied by the permittivity in free space. Now also the current density is equal to the conductivity and the electric field. It's important to note that this would mean actually that the gradient, that the curl of the magnetic field is equal to electric field all multiplied by the conductivity j omega epsilon permittivity, and this term is usually referred to as j omega complex epsilon, which is the complex permittivity, and complex permittivity is equal to the epsilon minus j conductivity over omega. This wraps up today's mini tutorial. Thank you for listening, and I'm Dr. Naveed Jabbar.